So today we're going to talk about verifying trig identities, and there are some helpful hints for you in verifying those identities. So first you're going to rewrite the more complicated side of the equation so that it is identical to the simpler side. And as you select substitutions, keep in mind the side you are not changing because it represents your goal. So we're only going to work one side of the equation. Now keep in mind, verifying identities is not the same thing as solving equations. Do not work both sides of the equation. Only work one. So let's take a look at example number 1. Cotangent theta plus 1 equals cosecant theta times the quantity of cosine theta plus sine theta. All right, so the right-hand side looks more complicated. So let's work that side first. One of the easiest things to do is to get everything in terms of sine and cosine. Well, we know cosecant is the reciprocal of sine. So we can change the cosecant to 1 over sine, and then the inside of the parentheses just stays the same. Now we can go ahead and distribute this. Okay, and then the last step is, well, what is cosine over sine? Cotangent. And then what's sine over sine? 1. Anything divided by itself is 1. And now you see we've gotten the same thing on both sides of the equation. So that is verified. Now let's take a look at example number 2. We have tangent squared theta times the quantity of 1 plus cotangent squared theta equals 1 over 1 minus sine squared theta. And both sides are kind of complicated, but because this is already in terms of sine and cosine, let's work on the left-hand side. All right, so tangent squared, when we distribute this, well, actually, let's not distribute it first. Do we know what 1 plus cotangent squared is? Think about your Pythagorean identities. Yeah, that's the same thing as cosecant squared. Now, when you're working these problems, keep in mind that there are more than one way, or there is more than one way, to verify these identities. You might use one set of identities to show that it's true, while somebody else might use a different set. So there isn't just one right way to work these problems. So keep that in mind as you're working. All right, so then we can take these and turn them into sine and cosine. So tangent is sine over cosine. So remember, because it was tangent squared, it needs to be sine squared over cosine squared. And then cosecant squared becomes 1 over sine squared. Okay? And then your sine squareds are going to cancel out, and you get 1 over cosine squared theta. Now remember, with Pythagorean identity, we know that cosine squared is the same thing as 1 minus sine squared. So now you have verified that one. All right, so now let's take a look at example number 3. I would say the left-hand side looks more complicated because we have some fractions in there. So what could we do first? Well, since we have multiplication in the denominator, we could separate those fractions. Then we can change everything into sine and cosine. Okay, now we're getting into some complex fractions, but that's okay because we can easily get rid of those. So when you divide sine over cosine by sine times cosine, that's really like saying we're going to multiply this by 1 over sine, not sine squared, 1 over sine cosine. And then the same thing over here. When you're dividing by this, it's the same thing as multiplying by the reciprocal. So if we do that, we end up with sine over cosine squared, and then sine. And then here we end up with cosine over sine squared cosine. Oh, forgot my theta. All right, so then you can see that your sines are going to cancel, and you could have done that up here in that step. That's okay. And here your cosines are going to cancel. And so here you're left with 1 over cosine squared theta minus 1 over sine squared theta. And then we're trying to get here, but what do you notice about 1 over cosine? It's the same thing as secant. So this is going to be secant squared theta minus cosecant squared theta, and that's what we were trying to get in the first place. So that one is verified. All right, so let's take a look at example number 4. Now, in this case, you could work either side. They're both kind of equally complex. But let's take a look at the left-hand side because it has a denominator that has a sum in there. So remember back to Algebra 2 when we dealt with radicals, and we had something similar to this, and we were trying to get rid of the middle term. So what could we multiply this by so that it would be a difference of squares? Okay? And when we want to have a difference of squares, it's going to be exactly the same thing, but we're going to have a plus in the middle. So we're going to multiply this one by 1 plus sine theta, put that in parentheses, and then whatever you do to the denominator, you have to do to the numerator. And now we can go ahead and multiply. Now, because I want 1 plus sine theta there at the top, I'm not going to go ahead and distribute those, because maybe I can get that cosine to cancel out. So I'm going to have 1 plus sine theta times cosine theta. And now we're going to use a distributive method to multiply these out. So 1 times 1 is 1. 1 times negative sine is negative sine theta. Sine theta times 1 is positive sine theta. And then positive sine theta times negative sine theta is negative sine squared theta. All right, now, what do you notice about the signs on the bottom? Yeah, you have a negative and a positive, so they're going to cancel out. So now we have 1 plus, sine theta, that's ugly, let's fix that. 1 plus sine theta times cosine theta, all over 1 minus sine squared theta. All right, now let's look back at our original problem. All right, we have 1 plus sine here. So let's see what we can do here to maybe get that to be cosine. Well, think about your Pythagorean identities. 1 minus sine squared theta, that's cosine squared theta. Oops. Helps to simplify it. There we go. Now, can we simplify this a little bit further? Yeah, we can cancel out that square with that cosine. So now, scoot that up a little. Now we're left with 1 plus sine theta over cosine theta, which is what we were trying to find.